Thank you very much, Ross. Thanks, Evan and team, for inviting me. It's a pleasure to be here. As you all just heard, my name is Anastasia Yendiki. I'm an investigator at Mass General Brigham and an associate professor at Harvard Medical School. And my lab is based out of the Martino Center for Biomedical Imaging in Charlestown, Massachusetts. And the goal of the lab is to develop technologies for imaging the wiring of the brain, the human brain, with the ultimate goal to be able to better understand how our brain circuits work in health and in disease. We do this both by using MRI scanners for scanning live human subjects, as well as you'll see later on, microscopy techniques for imaging postmortem human brains to go to even higher resolutions. To this end, I am currently leading a consortium of 9 institutions, including our own, that received a $25 million grant from the NIH Brain Initiative to develop capabilities for data acquisition and data analysis with the ultimate goal of producing the most detailed map of the wiring of the human brain to date. And our project, the LINC project, the Center for Large-Scale Imaging of Neural Circuits, is part of a larger $150 million consortium funded by the NIH, the CONNECTS, or Connectivity Across Scales consortium. And I also co-lead a data coordination center within the greater consortium to facilitate the computational aspects of this consortium, which is expected to produce petabytes of data in the next few years. So what would we like to see? We would like to see something like this. This is what our brain looks on the inside. So if you open a postmortem human brain, you'll see these bundles of microscopic fibers. Each fiber is more than 50 times thinner than a human hair. And so we do not obviously have the resolution to image this with an MRI scanner. However, we do have a technique to get sort of a rough idea of how our brain is wired. This is called diffusion-weighted MRI. It's a series of scans collected in a regular MRI scanner, and we can analyze it to give us an image of the wiring of the brain that allows us to see sort of the big highways of the brain, but we know that we're not getting all the details right. Why do we need to get the details right? Because these fiber bundles are important to reconstruct in order to be able to target them with neuromodulation therapies, and in particular with deep brain stimulation. This is a technique where electrodes are implanted deep inside the brain to target specific fiber bundles and to stimulate specific fiber bundles. And it's well known that it's important to know which fibers exactly to target with the electrodes to get the therapeutic effect that we want for the specific disorder that we're targeting, and also which fiber bundles to avoid side effects. This is a therapy that is becoming well established for motor disorders like Parkinson's and dystonia, etc., and also more and more investigated for psychiatric disorders like depression and obsessive compulsive disorder, but even beyond that for epilepsy, Alzheimer's, etc. And so the best thing we have right now to be able to target these sort of interventions in human subjects is either a noisy MRI scan that we can get from by scanning someone in a regular clinical scanner for about 10 minutes. Or if we want something cleaner and more detailed, there are synthetic models that come from information that anatomists have gathered by doing detailed animal studies and figuring out how these fiber bundles look in animals and sort of trying to extrapolate what they would look like in a human brain. You can see that this is pretty artificial. So ideally, we would like to have a very high resolution, down to the resolution of single fiber image of what these circuits look like in the human brain. And this is where we're trying to go with the LINK project. And as I said, we're a consortium of 9 institutions, and we're imaging the same postmortem human brains at resolutions that range from about 400 micron with MRI in the whole brain down to the submicron level with several optical and X-ray microscopy techniques. These types of imaging techniques, if applied to large volumes of the human brain, will produce petabytes and petabytes of data. And so we are also tasked with developing AI tools to be able to better and more efficiently mine these large amounts of data. And what will we get once this project is finished? So we're already starting to get the first data. This is the highest resolution MRI scan of human brain connections to date that we acquired here at Mass General Hospital by scanning a postmortem human brain for an entire week. So ideally, we would like to have this quality of data in the scans that someone can get in the clinic by scanning a human subject for 10 minutes. So by having both this high quality MRI and the microscopy data to provide us the ground truth, we hope to be able to train AI tools to be able to extract this sort of high quality information about the connections in the brain from a regular clinical MRI scan. And ultimately, we would like to have better models for targeting neuromodulation, a better, more accurate, more detailed map of the connections in the human brain that are relevant to psychiatric and neurologic disorders. And ultimately, these data will allow us to better understand the information flow in the brain that allows us to accomplish all our daily functions and better understand how our brain is so much more efficient at completing all these tasks than a computer. And I will end here. Thank you very much to the LDV team and to all of you for your attention. And I'm happy to talk to any of you more offline.